All right. Welcome, everybody, to our panel Q&A, the place for you to get all of your questions answered about space. So, once again, my name's Denise, and now I'm going to turn over the microphone to our panelists to just briefly introduce themselves. Oh, actually, here, let's use this microphone.
Hello, can you hear me? Yes. So, I'm Michael. I'm a third-year graduate student in astronomy. I'm doing research on exoplanet atmospheres, but you can also ask me about supernovae. I worked on that a bit. Yeah.
Hi, I'm Nicole. I'm also a third-year graduate student, but in planetary science, which is actually just across the street. Yeah, you can also ask me questions about exoplanet atmospheres, or direct imaging, or planet formation in general.
Hi, I'm Reinier Jansen. I'm a postdoctoral researcher. We're both here and at the Jet Propulsion Lab. And my field of research is galaxy evolution and how that is affected by supermassive black holes and the instrumentation you need for both that and other observations.
All right. So, questions?
Currently, there is no robust technology in existence for any kind of reasonable space travel. Do you know of any thought being devoted to non-fringe, non-crank ideas that may contemplate how that may be possible, or is there any hope whatsoever? Any group or name that you know of that is thinking about that?
Do you mean travel to other stars?
No, even just a long distance is good enough.
Right. So the main obstacle to traveling to nearby stars is that they're really far away. The nearest star to us is 4 light years away. So even if you're traveling at the speed of light, which is the maximum you can possibly travel at, it's going to take you 4 years. Now, if you travel at 10% the speed of light, which is still 30,000 kilometers a second, it's going to take you 40-something years. The problem is, with chemical rockets, the maximum exhaust speed of the gas is something like 4 kilometers a second. There's a rocket equation that says the amount of fuel you need for a rocket to go to a certain speed goes up exponentially with the speed you want to go to. So if you want to go to even 1% the speed of light with a chemical rocket, you need more fuel, you need more mass than exists in the entire visible universe. And by the way, that's not by a little bit, that's like by far, by a factor of 10 to the 200. So there's no way that's ever happening. And actually, chemical rocket engines have not really improved since the 1960s. Yes. Yeah, chemical rocket engines haven't improved since the 1960s in terms of their exhaust speed, because that's limited by the fundamental laws of physics. When you have a chemical reaction, you're basically shuffling electrons around. That gives you a typical energy of a few electron volts. An electron volt is a unit of energy. A few electron volts can accelerate a molecule to a few kilometers a second. That's why, like, all of the bullets, all of the artillery, they're limited to a few kilometers a second. So what we want to increase the exhaust speed. The best way to do that is by going nuclear, right? Because nuclear energy densities are millions of times greater than chemical energy densities. So they can get you up to speeds that are thousands of times greater. Now, you asked about non-fringe proposals. There's actually one from the 1960s, which is completely crazy, but yeah, it's the only thing that that's even remotely close to being feasible, and that's Project Orion. What Project Orion is, the idea is you build a super big spacecraft, something like the size of a small town. You store thousands and thousands of nuclear bombs. You throw one out the back, you explode it.
That's crazy, right?
This is the least fringe idea. This is the only proposal that's possible with current technology. And I'm using a very generous definition of possible. But yeah, if you use fusion bombs, this can get you up to something like 10 to 20% the speed of light. So you'll be going to Alpha Centauri in, 30 years.
Okay, so what about using lasers? Because I've heard about sending a bunch of tiny probes, accelerating them with a laser to get them up to, say, a quarter of the speed of light, in which case you could get to Alpha Centauri or the Centauri system in 16 years? Yeah, something like that.
Yeah, so when I talked about the rocket equation, I was assuming that you carry your propulsion with you. If you're accelerated by an external source, the rocket equation doesn't apply. So yeah, you're right. That's one of the proposals. It's called Project Starshot. But that proposal involves probes that weigh a few grams. Because by the time you get up to kilograms or tons, there's no way you can possibly produce that much energy. Yes, yeah, that's a proposal. You send hundreds of them. But if your probe is only a few grams, well, first of all, you have no way of slowing down at the other end. So you're passing by this system at relativistic speeds, and you're hoping that you can measure something, in the few minutes that you have. The other problem is, with a few grams, like what can you put in there? Can you put a camera? Can you put instruments? Can you put a communication antenna? Paper clips? Yeah, you can put paper clips. Yeah, so that's a daunting engineering challenge. The other problem is, how do you keep this thing aligned? How do you keep the spacecraft aligned with your laser beam while it's accelerating? Because it's accelerating with thousands of Gs. So these are extremely big forces that you're putting onto basically a solar cell, onto a piece of metal that's supposed to catch the laser light. So yeah, it's a daunting engineering challenge. I wouldn't say it's impossible, but it's very difficult.
So in terms of profiling what the atmospheres or things at certain exoplanets, how are you doing that if you're not doing direct imaging? Mm-hmm. Are you inferring certain things, or?
Yeah, there's actually a couple of different ways that you can sort of probe exoplanet atmospheres. So there's the obvious way, which is direct imaging. If you have light from a source, you can then characterize that light. So that's kind of the most obvious way. But you can do something called transmission spectroscopy. So when a planet passes in front of its host star, some of the light from that star has to pass through the planet's atmosphere. So that actually imprints that signature of that planet. So that's one way. And then when the planet's actually behind the host star, you're missing that planet's light. And you can then characterize that light as well to try to understand what the atmosphere is comprised of. So that's kind of the secondary way, sort of the least obvious way, but actually the most fruitful way. Most exoplanet atmospheric characterizations have been done through transmission or what's called thermal emission, when you're just taking that planet's light in terms of numbers.
My question is how long does it take to discover a new planet? I saw the graphs moving so fast. So from the time you get the data to confirm how long and what process happens in between. Because that's what I'm really interested. Someone has to approve ourselves, right? Someone sees the data, someone has to approve. What is the procedure there?
It's really dependent on the method that you're using. So the detection method is really what's going to be that stopping point. So for direct imaging, for example, there's been tremendous efforts that have been put forth to try to sort of probe all the local stars to see if we can detect a planet. And it takes a tremendous amount of time on these telescopes to try to get planets. There aren't that many directly imaged planets, but things like TESS, the Transiting Exoplanet Survey Satellite, I believe is what that stands for, one of those astronomy acronyms that actually works for a change. So there is actually a pipeline, an automated pipeline that's being used by them, similar to what Kepler does. So kind of you can almost analyze it, not quite in real time, but you can get candidates rather quickly because it's all been automated. RV, which was alluded to before, takes longer because you need to have a baseline. You need to keep taking measurements of the star to keep seeing the radial velocity shifts. So it kind of depends on the detection method, basically. Oh.
So I should say that for test planets, if you see them transiting with this satellite, often we have archival data of historical radial velocities. And if you see the same planet with the same period and the same phase in the radial velocity data, you can be pretty much certain that it's a planet, because now you've detected it in two independent ways. So if you get lucky like that, then you can confirm a planet as soon as TESS releases the candidate.
And sort of in order to actually be certain that it is a planet, or at least be sure to a certain extent, you want to at least have two transits of the planet. So it's at least the period of the planet times two, or depending on when you catch the transit. So that's kind of the lowest limit on that. But most people generally want more than that, depending on the period of the planet. But yeah, like I said, it kind of depends on the detection method.
I'm wondering if there's any value in comparing the model of, say, particles expanding away from an explosion to the universe expanding after the Big Bang. I'm wondering how we can, if there's anything to melt those two ideas together.
I think I'm not a cosmologist, but I think there's so much inherently different physics there that comparing molecules from an explosion here on Earth, that's governed by your gas laws, and those laws are inherently very different from the laws which were dominant in our early universe. So in our early universe, it was mainly gravity, and these strange forces, dark matter, dark energy, which we actually don't know enough about to say how they react, maybe dark energy does follow some gas law, and maybe it does map like this, but we don't even understand what this dark energy is. So from that point of view, I'd say no, for now, whatever happened at the Big Bang, that is computer simulations, theories, equations that are not resembling to anything we have simple here on Earth.
Yeah, so the expansion of the universe is the expansion of space. When you have an explosion on Earth or even in space, that's an object exploding, within space. That's not space itself expanding. Yeah, there's a fundamental difference between the two.
Rainier, could you speak about instruments and terrestrial base versus instruments that are being built for spacecraft, what the limitations are in materials, weight, energy, that kind of thing, what they're detecting, electromagnetic, optical? I mean, how much of that are you involved in?
I'm involved in various things, but or have been over my career been involved in various things. So the first obvious thing to look at is, so most of astrophysics is doing electromagnetic radiation, so light. And if you look at the electromagnetic spectrum, which includes everything from radio wave, infrared light, the radiation your microwave uses to heat up your food, but also UV and X-ray. So the first obvious question is, can we even use telescopes on Earth? Because luckily for us, X-ray radiation doesn't penetrate the atmosphere. Gamma ray radiation doesn't penetrate the atmosphere. Most of the infrared radiation doesn't penetrate the atmosphere. So only optical light, so the visible light we can see with our eyes, and radio waves. Those are actually the two wavelengths we can properly see from Earth. Now, if we go to very special sites, usually what we call high and dry, the Atacama Desert in Chile, which is 5 kilometers, so that's about 15,000 feet altitude. It's extremely dry there. Similar Antarctica, you wouldn't say it's dry there, but all the water there is frozen out. So all the water is out of the air because it's so cold, their infrared radiation can actually penetrate down to Earth for a long while. So that's your first question. Can we even see stuff on Earth? Then the next step is, how big a telescope do you want? Typically you want a telescope which is as big as possible, because the larger you make your telescope, the smaller the details you can see. And of course we want to have usually as detailed an image of the sky as possible. But then you run usually quickly into mass problems, because you cannot very easily launch an enormously big telescope into space. Now, recently there's been a lot of advancements in this, that we, for example, the next generation space telescope, the big James Webb telescope, that's a 6-meter diameter telescope. But it actually consists of 7 different bits which are folded up and will be folded out into space. So that's the way you circumvent already some of these issues. But still, it's how much weight can we launch into space? And then the next step is, how much energy do you want to allow this? Because everything you put on your spacecraft needs to be powered by solar energy and by solar panels. So usually it's constrained by mass and energy. That's the 2 main constraints for satellite missions. And then on the ground you can basically, within the structural limits of buildings, so to say, you can build as large as you want.
I wanted to ask Nico a question. Which of the future telescopes are presently the ones being planned now? Which of those has the best chance to detect planets directly? And what are the prospects for the James Webb telescope?
So one of the big telescopes, it actually is really big, that's going to be most important actually are the giant telescopes, like the TMT, the 30-meter telescope, for ground-based direct imaging. So as was kind of alluded to before, for direct imaging, you really want to be able to disentangle the light from the planet and the star, and the bigger the telescope, the better you are able to spatially resolve those. So I think one of the big things in terms of ground-based surveys that's really going to help you, really ground-based instruments that's really going to help for direct imaging are these giant telescopes on the ground. We're also having, after JWST and after WFIRST, there's a couple of mission proposals for HabEx and LUVOIR, these giant space telescopes. So those will be able to, for example, HabEx will be able to directly image planets. So that's kind of in the future, will be really great for direct imaging. Depending on the mission that's accepted, it could have a starshade, it could have these giant sort of petal things that flies far away from the telescope and blocks out the light physically from the star. It'll have a coronagraph, so that's, I think, kind of the far future. But between sort of those missions and the giant telescopes we'll have on the ground, that'll really be the boom for direct imaging, in the same way that these transiting satellites that have looked at transiting planets, Kepler and TESS have done for transiting planets. JWST I'm very excited about, mostly because of what it's going to do for exoplanet atmospheric characterization. So we'll be able to directly take, well, direct is a relative term, but we'll be able to get light from the host stars that have been, like I talked about before, planets affecting that light, and we'll be able to resolve molecular features in a way we haven't been before for smaller and smaller planets. So kind of looking at different things like water and methane and CO2 and things like that, they'll actually be able to get direct observational detections of in a way we haven't before. So it's kind of a different side of exoplanet detection versus characterization. That's, yeah.
So many people will remember that when the Hubble Space Telescope was originally launched, it didn't work, and it was blurry, and they had to fix it, and that entailed astronauts on the space shuttle, capturing it and fixing it. if you know, I didn't think about this until you just were talking about it, the James Webb Space Telescope, when it's launched, and with these moving parts, like having to unfold the component parts of the mirrors, what contingency is there if it doesn't work because we don't have a space shuttle anymore?
And we wouldn't be able to get to it anyway is the other thing. It's so far away we wouldn't be able to get to it. I have heard that if something, I'm not sure how true this is, but I've heard that if something were to go catastrophically wrong, there's enough fuel on the instrument to send it back to Earth orbit. I don't know how true that actually is, but that's what I've heard. It's not a great plan in general, but there's been a ton of work that's been done on the ground testing this instrument, testing the way it unfolds, and I think it's hard when you hear a lot of things like, oh, this got pushed back in the news and things like that, but just know that a ton of effort has been put into making sure that this telescope works the way the community and everybody really wants it to. So, yeah, it's hard, but I'm thinking that all of these pushbacks and all of these testing is really kind of reassuring me, at least, that everything has been done to the best of our ability at the moment to kind of make this amazing instrument that's never been done before. If you think about the scope of what's being done and how far it's going to be out and what it's going to do for our just science, it's kind of amazing to think about. So it is scary, but I have hope in the engineers, but I'm also not an engineer. So, yeah. Technology's gotten a lot, it's really advanced since then, though, is the other thing. Since Hubble was originally launched, we kind of know a lot more about how to design these sorts of spacecrafts, and we've had a lot more of these types of telescopes in space. So we learn as we go.
So yeah, the other difference between the Hubble and the James Webb is that the Hubble was specifically made to be serviceable. Because people at the time knew the shuttle existed, they knew the astronauts were capable of making repairs. So they designed the Hubble in a way that it was fixable. The James Webb is not fixable. If anything goes wrong, then we lose it. 100% guaranteed.
Be more optimistic than that.
She just said be more optimistic, but no, we do. That's usually what happens with spacecraft.
It's true.
Maybe I can add.
Yeah.
Maybe I can add something to that. What you can also think of is the following: it's all this technology for building something like James Webb has been developed now over the past 20, 30 years. It is usually what's in space is very old because it needs to go through so much rigorous testing that it's at least 5 years old. But things like James Webb, there's so much, the cost of development is so high that if something would be happening to James Webb during launch or during deployment, the extra cost of just building a duplicate, figuring out the problem, building a duplicate and launching the duplicate is much lower than rebuilding James Webb. Like the current cost of James Webb. And I'm pretty sure that in the case of James Webb, the community, the astrophysics community, would pull together the money to build number 2. Because a few LUVOIR and HABAC's future missions were mentioned. These missions are basically already copies of James Webb optimized for slightly different things. So if there is a bug, they're going to fix it. And there still is missions which go wrong because of things you would imagine we should have figured this out long ago. One of the recent Japanese X-ray missions was launched 2 years ago. 2 years ago. They got amazing data back from the spacecraft, and then they gave it the command to go to its first science target, and the thing started spinning. It started rotating around its axis, faster and faster and faster. What somebody had done, somebody had put a minus sign in the code. So instead of when it started rotating, slowing down, it started rotating, started moving faster. And it spun itself into bits. And they're now building the exact copy, which will be launched soon.
So astronomy is going through its decadal survey right now. What's at the top of your priority list? Like, what would you like to see be prioritized at the top? Also, if you want to answer this one too, because you're in it.
I'm a cosmologist, so my bias is toward cosmology. For anybody that may be unfamiliar with the term cosmology, that's the study of the universe on very large scales. So anything larger than a galaxy, basically, is cosmology. So I'm very excited for W first. That's something that I'm hoping will be prioritized in the upcoming decadal survey, which it has been ranked very highly in the past. So I'm hopeful. There were some funding issues for political reasons, I think, with W First recently, but it seems, fingers crossed, that we've come through that on the other side. Okay, so that would be my preference for something to prioritize.
I think for me, if you want to prioritize, is one of the future missions called the Origin Space Telescope, which is a large far infrared telescope. And one of the nice things about that wavelength range is that you can, what I would always call is the other half of the universe. Because with our own eyes, with invisible light, we can see a lot of galaxies. But about half the galaxies in the universe we cannot see in the visible light, because there's so much gas and dust in these galaxies that all the visible light is absorbed and re-emitted in the far infrared. So I'm really interested in these dusty galaxies, because there's a lot of initial starbursts, initial evolution going on. So I would really like this Origin Space Telescope to go on.
So I think mostly what I prioritize is just exoplanet atmosphere characterization in general. So I'm a planetary scientist, which means mostly, in my particular case, I'm concerned with how planets form and evolve. And one of the sort of hallmarks for how these planets form, and kind of the way that you can understand where in their sort of protoplanetary disk they form, are by their atmospheres. What these planets accrete and how they accrete them is fingerprinted in their atmospheres. So if we want to understand the way our solar system formed, kind of the easiest way statistically in terms of numbers is to look at just tons of different planets' atmospheres and try to understand how those planets formed in their disks.
So yeah, I'm most excited about a proposed mission called LUVOIR. I don't actually know what the L stands for, but UV stands for ultraviolet, O is for optical, IR is for infrared. And this is a true successor to the Hubble Space Telescope. The Hubble Space Telescope is 20-something years old by now. Its gyroscopes are failing, so it probably doesn't have all that many years left. And also, we don't have the shuttle anymore, so we can't just go up and fix it. And when we lose Hubble, we're going to be severely limited in our ability to do UV astronomy. Because UV, especially the far UV, is not accessible from the ground. The atmosphere simply blocks it. It's only possible from space. And that's what makes Hubble right now the best instrument to do UV astronomy. LUVOIR will be able to do that. But more than just being a successor to Hubble, that's much, much bigger. There's two versions. One has an 8-meter mirror, one has a 15-meter mirror. HST has a 2.5 meter mirror. Yeah, 2 meter mirror. But the thing that's really exciting about LUVOIR is that it's going to have the ability to directly image Earth-like planets around Sun-like stars. Earth-like planets in habitable zones around Sun-like stars. So this will really give us the chance to detect biosignatures around Earth analogs, which we definitely don't have the capability right now. And with the next generation of instruments like JWST, if we are really, really optimistic, it might be able to detect some biosignatures in planets around very small stars, but definitely not around sun-like stars. So yeah, I'm very excited about LUVOIR if it ever, gets funded.
Has there been any thought yet about, with SpaceX's new BFR rocket, you've got a 9-meter payload size. Does that all of a sudden open up a whole set of new options in terms of very large telescope design?
Mm-hmm. Yes, because because the current fairing. I don't know the largest current fairing, but basically the SpaceX rocket is not only the ring is bigger, but also the lifting capability is higher. So just the volume and mass that you can send up becomes bigger, and that inherently means you can build a bigger telescope, which there's almost never a reason to go for a smaller telescope, I think. So yes, there will be new options, but I think the current state is now always that you design for the largest currently available rocket which you can afford. So I think that you can afford will in the end also become the crux.
Hi, Reiner, my question for you is, I'm sure you're aware and excited about the news about that black hole at M87 discovered. I was wondering if you could maybe speak to, if you know more about the type of computational photography, I guess you could even, I don't know if you could use the word photography for that, and maybe how applicable that might be to other objects that we could observe, and maybe how we could expand on that. It's obviously pretty new technique, as I understand, but where do you see that going, and how maybe we could apply that to, how does it apply to black holes and other objects? Yeah.
So, it's great news, and with that I want to advertise that you should take one of the flyers when you go away, because for the next semester we're trying to get Katie Bauman, who was one of the people working on that. We're trying to get her as a speaker the coming semester, so keep your eye out for that. So how can we? To image a black hole, which is extremely small at an extremely large distance, we need an extremely big telescope. And so what we do is we basically make an artificial telescope by combining information from telescopes on different locations on the Earth. And as such, we construct a virtual telescope the size of the Earth. What we then do, you combine this information. It takes an enormous amount of computing power, especially given the large amount of data that is required to create this image. And then we can get these amazing images of the shadow of the black hole. What else can we do? Well, the technology they've been using for this, which is called interferometry, is not necessarily a new technique. It's been used for a very long time. Basically, most radio telescopes or most large radio telescopes are interferometers. And they've been used to study AGN. When they accrete, they create enormous radio plasma, so radio emission from that. And a recent interferometer is ALMA, which is working at millimeter wavelengths. And one of the main things ALMA has done is it has imaged young planet-forming systems. So it can image the dust rings around stars in which new planets are forming. But also it can resolve, as I said, I'm highly interested in the obscured universe. It can resolve the individual galaxies, while the space-based smaller telescopes will not be able to do that. And then,
this is maybe a bit off topic, but interferometry is not just possible in the radio waves. It's also possible in the optical. And in fact, Mount Wilson, which is very close to us, there's an interferometer called Chandra. This is basically a few telescopes where the light from the telescopes is physically brought together and interfered. And you can measure the interference patterns, and in that way, you can make an image of very small things. Now, one of the things that Chandra has imaged that's very cool is the surfaces of other stars. Right? You don't think about that. Like we can see our sun in extreme detail, but with Chandra, you can see other stars. You can see how oblate they are. Some of them are quickly rotating. You can see star spots. And the most incredible thing is that this technique to image other stars was first applied over 100 years ago. Now, 100 years ago, they couldn't make a map of normal sun-like stars. They could only image giant stars. But nevertheless, they managed to measure the diameter of, I think, Betelgeuse in the 1910s.
Hello. I came in late, so maybe I missed this question earlier, so forgive me if it's redundant. But I was at the young woman who spoke tonight talked about infrared radiation as a property of living organisms. And I was wondering if it's practical to look for infrared radiation on exoplanets as a sign of life?
Mm-hmm. Right. So not directly. If you're thinking about the heat generated by organisms, that's much too faint to detect with current technology or even far future technology. But the thing that's interesting about infrared is that most of the spectral features from molecules are in the infrared. So, for example, water has the strongest spectroscopic signatures in the infrared. So does carbon monoxide, so does methane, so does pretty much every molecule you can imagine, with only a few exceptions. And that's, again, a property of fundamental physics. These spectral features are due to transitions between rotational and vibrational states. And those states tend to be low energy. Transitions between low energy states are themselves low energy. That's why they're in the infrared. So yeah, actually, there's a type of work. Well, okay, so JWST, the main region that is so good, well, one region is that it's a big telescope. Another region is it has a huge spectral range in the infrared. It can see all the way from 0.5 to 30 microns. And that's the main region that is so good at characterizing exoplanet atmospheres.
So Michael kind of alluded to a possibly sort of easier way is biosignatures, looking at the atmospheres of these planets. So possibly instead of looking for just sort of the direct thing, living thing in the light that they're giving off, you can look for sort of the atmospheric characterization, things that happen to the atmosphere because of what we've done, for example. So you can look for biosignatures. There has been some work that's been done on trying to see what the atmosphere of an exoplanet would look like if the civilization had destroyed itself due to like nuclear war or something like that. So there's been some work that's kind of like, what can we detect in sort of these ridiculous situations? So a lot of that's just based off of trying to take the fingerprint basically of the planet's atmosphere.
Right, so the most ridiculous idea I've heard in this regard is something called Dyson Spheres. This idea is, so suppose you have a civilization that's very powerful. They want to capture the entire energy output of their star. So they englobe their star in a sphere of material. So they capture all of the light from the star. They use it up somehow. They emit it as waste heat. The waste heat heats up the sphere that they build, and this will glow in the infrared. People have actually looked for this. They haven't found anything. But who knows? Keep on looking.
This question is actually for our roving cosmologist here. I'd like to ask, what's the probable ultimate fate of the universe, and how sure are cosmologists that that's the answer?
Good question.
Yeah, so that's a great question. So what we think right now, we're limited by the precision of our measurements. So I guess in some sense we can never be 100% certain that this is the case, but to the precision that we can currently measure it, what we think will happen is that our universe will expand forever. So I guess I can doodle on the board a little bit. So if this is time, and this is something that we call A, this is called the scale factor of the universe. This is just a number that parameterizes how the distance between 2 points at a certain point in time as compared to previously. There are equations we have, from Einstein's theory of general relativity and Newton's laws of motion and so on. We can use these equations to describe what the behavior of this number should be as a function of time, and to the precision that we can measure it, we think that it should continue to increase forever. Now that said, it could be that our measurements are not yet sensitive enough to detect the fact that the universe will be, that the properties of the universe determine that it will ultimately, imperceptibly slow down its expansion and ultimately begin to contract in the future. But for now, this is what we think.
I'm not sure if you're familiar with the term, but I came across something called phantom dark energy. Could you explain what that might be?
I have never heard the term phantom dark energy. Do you recall what this was being used to describe? Expansion of the universe. Well, I can certainly talk about dark energy. I'm not familiar with the idea of phantom dark energy. Well, so dark energy is kind of just a phrase that's used to describe a phenomenon. And this phenomenon is observable, and we know it exists in the sense that the expansion of the universe is accelerating. This has been measured. It won the Nobel Prize in 2011. And so dark energy, the reason that the term dark energy is in use is because this accelerating expansion is consistent with being caused by some unknown form of energy permeating the universe. And we can measure what the properties of this dark energy would be if it is indeed some new type of energy permeating the universe. But we don't yet know if it is indeed energy in the sense that we understand energy, or if it's due to some other type of cause. So the phenomenon that we call dark energy could be caused by modifications to Einstein's theory of general relativity. And so that could be another reason that we observe these properties that are consistent with a new form of energy. So I guess the answer to the question, is all dark energy phantom, is, well, what do you mean by dark energy? Do you mean this observable phenomenon which definitely exists, or do you mean the hypothesized energy density permeating the universe, which we don't know if that exists or not? Does that answer your question? Yeah. Okay.
Recently, Caltech dismantled their helium recapture facility that was over across the street. Do you know of any other facilities around, and if you had detectors and that sort of thing to test under liquid helium, where would you go?
So you can still order barrels of liquid helium and barrels of liquid nitrogen. Very expensive, yes. So what is generally happening to cool detectors is you go to cryogen-free systems. So it's basically usually what we call pulse tube coolers, which uses a closed system of helium, which under different pressures can extract the heat.
What's the largest mass that you would be able to cool down to
So you can, as long as you make your pumps large enough, you can cool fairly big masses. So the pulse tube cooler is just the main limit of the pulse tube cooler is your compressor. So as long as you can make your compressor physically bigger, you can cool bigger things.
2-3 pounds realistic?
No, much more. So, as an example, the cooling power of a cryostat, which I used during my previous postdoc, it could cool it could cool 10 kilograms, so that's 20 pounds approximately, to 8,000th of a degree above absolute zero. And that's without any liquids, and it could do that within 24 hours. So within 24 hours from room temperature to this extremely low temperature. Huh? So this is a, let's say, commercially available system. But also, this is extremely low temperatures. Imagine these pulse tube coolers they're commercially available, and they're at more places than you might think. If you are going in an MRI scanner, that scanner is already cooled by a pulse tube cooler. And those machines are not small.
So you talked earlier about interferometry as the method by which the black hole was observed or imaged. And then you talked about interferometry for optical for visible light, and that the light was interfered. In this context, what is the definition of interfere and interferometry? Because it sounds like it's a little bit different than like the way we would usually use that verb in normal non-scientific context conversation.
I can take this one and doodle on the board if you like.
Yeah, it requires the board, that's right. Yeah, so that's indeed the simple version. So light, as you know, is a wave. And a wave, as he drew it, if you stack two waves properly, then like this, like the hills of the wave are at the same moment and the valleys of the wave are at the same moment, then you get a bigger wave. However, if the hill of the first wave meets the lower point of the other wave, then they cancel out. And now, what is the trick? What you usually see in interferometry or in water, when you throw two rocks in a pond, you see this. So if I drop my rock here and I drop my rock here, then the crests of the wave will be here. The next crest of the wave will be here. The next crest of the wave will be here. And you can already see that we will start getting points where we will have crests coinciding, and locations that should be a long time since I've did. Well, if you see this, there's distances where at the same time the crest will arrive, and you will have an extra large crest. And there will also be distances which, and this distance is basically, so crest 1, crest 2, and this is coming from the bottom, so like this. So of the number of wavelengths, so the time it, or the distance it takes for a wave to go up and down once, if those distances match, well, if there's an integral number of distances between them, then we have constructive interference. So we have an extra strong signal. However, in the same vein, if we had a this point, for example, here we could imagine that the waves destructively interfere. So the crests and the valley arrive at the same time, and so we have flat water. Yeah, so it's a pattern of crests, of extra high crests and basically statics, which you can create because at one point the waves arrive what we call in phase, so they arrive in sync, and at other points they arrive out of sync.
But the ultimate end of it is that you get a magnification of whatever it is that you're measuring, and that's why you use like 7 different telescopes around the Earth to look at this black hole and combine them set together.
Yeah, so what basically happens when you look at space, you observe exactly, so this is water in a pond, but we observe exactly the inverse effect. So we see light arriving here and light arriving here. And what we try to figure out is if we're in the amplification stage or if we're not in the amplification stage, because that tells us something about basically this distance. How much extra time it took. And as you can already see, this point has this much extra distance, but if we now had a point here, that has an equal distance to both telescopes. Yeah, it's like a parallax. So basically by using multiple telescopes, we can figure out very exactly the position where light was coming from.
So here's an intuitive but very simplified picture of why interferometry works. Okay, so I'll use Okay, so you drop a stone in the pond, it emits waves. I assume that these are the peaks of the waves. Now let's assume that you want to know like where this thing is as accurately as possible, right? If you have a very small telescope, might look like this. You're not getting much information about the wavefront. You can't measure the direction very accurately. But if you can ask your friend who's very far away about what they see, so let's say your friend is over here, you ask them to record the shape of the wave at every instant of time. So then you can see, to them, this peak hasn't arrived yet. So that based on how long it takes for this wave, this peak to arrive at their position, you can reconstruct the shape of this wave, right? So you can reconstruct this curvature, and then you have a much longer baseline to tell the direction of this this source. Now, obviously, for this to work, you need to be able to measure the phase of the wave, right? If you can only measure how strong the wave is from peak to trough, that's not telling you any direction information. You need to be able to tell at every moment in time, is this a peak, is this a trough? If not, like, where in between am I? That's why this very long baseline interferometry only works for radio waves. Because for radio waves, we have electrical instrumentation that's fast enough to record the phase of this electromagnetic wave. For optical wavelengths, the frequency is something like 10 trillion hertz. There's no electronics you can possibly build that can record the phase of that wave. So what we had to do instead is physically bring the waves together and interfere them. And that's why that's the method that Chara uses.
Can interferometers ever become mode locked? I've heard this term, and I was wondering if you could expound upon it, please. Thank you.
I don't know the term, so that's okay.
Going back to expansion of the universe, could you explain a little bit about what they're measuring from, like, the Hubble Constant? Because I know that recently changed, and what exactly are they measuring, and how do they measure it?
Yeah. So the Hubble Constant, I'll do some more doodling on the board here. My favorite thing to do. So the Hubble Constant, we call this H0. And what this means is it goes into this equation. So in this equation, v is a velocity. That's the velocity of things that we observe moving away from us. H0 is the Hubble constant, and d is the distance from us. So what this means is that if this is us here on Earth, and we observe some galaxy at this distance, it's moving with some v, and it has some distance d. Now, Hubble's law, that's this equation, says that if we observe a galaxy that's twice as far away, it'll be moving away from us twice as fast. Now, this law is only valid up to a certain distance, but it's a very good approximation to the motion of galaxies in the universe within a certain distance of us. And so what we measure when we measure the Hubble constant is two things. We measure the velocity of galaxies along our line of sight to the galaxies, and the way that we do that is by using the Doppler effect, which is where the wavelength of light changes according to the velocity of the source of that light. If something is moving away from us, its light will be red-shifted, meaning the wavelength will be stretched out. So that's how we measure the velocity. And then we measure the distance. Well, that's a tricky thing to do. There are different ways to measure the distance. But most commonly, the way that it's done for these galaxies is by using something called standard candles. And what that means is we observe something such as a particular type of star or a supernova where we know the intrinsic brightness of that object. And so if we know the intrinsic brightness and we can measure the apparent brightness as we observe it from Earth, we can use those two things combined to find the distance, because something that's farther away will appear dimmer. And so that's how we measure the Hubble constant. We measure for a bunch of different galaxies, we measure their velocity moving away from us, we measure their distance, and then we plug them into this equation to find the Hubble constant. Okay, we can share. Oh, there might be another one.
Hello? Okay, good. Okay, so I think the reason the Hubble constant has been in the news recently is that there's this, if you look at that equation, h naught is one number. It shouldn't matter how close or far you are from the Earth. It shouldn't matter how early or late in the universe you are. H naught is one number and it never changes. Now, this group measured h naught in the current universe. So, within galaxies that are very close to us. They also measured h naught in something called the cosmic microwave background. This was in the very early universe. This radiation was emitted when the universe was 400,000 years old, and it had just cooled to below 3,000 Kelvin. At this point, electrons and protons combined to form neutral atoms. Right, that's the significance of this epoch. And the h naught that they got by measuring the cosmic microwave background is roughly 9% lower than the value in the local universe. Based on current physics, our current understanding of physics, that should not happen. There's a bunch of possible physical explanations for this discrepancy. I don't think any of them are really that convincing, or there's not, at least not that much evidence for them. So yeah, that's probably the news item you heard, and we still have no idea what's going on.
Well, I wouldn't say we have no idea. We have lots of ideas.
Yes, we have too many ideas about what's going on.
Most of our ideas are this group was wrong or that group was wrong.
Yes.
Because they did their measurements wrong.
Yes. But recently the discrepancy has grown large, like maybe too large to be explained by systematics.
So you mentioned earlier that the expansion of space comes from general relativity, and this h naught is also a measure of expansion of space. So is h naught experimental, thing that we found, or is it like derived from theory?
That's a great question. So h naught is a measured quantity in that the value of this quantity is measured. Now, the way that this ties in with theory, so we have an equation. It's called the Friedmann equation. And I will write it on the board, and then I'll explain it because it's a little bit complicated. Let's see. So this is the Friedmann. Actually, I don't remember if the negative signs are supposed to be there or not. I think they are.
I think so too.
Yeah.
Yeah, they are.
I'm pretty sure I wrote this correctly. Okay, so this is our Hubble constant h naught, and this is h of z. Well, I should write. I'll simplify this by writing h of t. Okay, so this is h as a function of time. So h here is basically the analogous quantity to the Hubble constant, but measured at each point in time, whereas h naught is that value as defined right now. And these numbers here, these omega m, omega lambda, and omega r, are numbers that represent the amount of energy in the universe from various sources. So this is the amount of matter in the universe, this is the amount of dark energy, and this is the amount of radiation, so light and neutrinos, basically. And then this A is the scale factor A describing the size of the universe. This is complicated. But the punchline here is this equation can be derived from Einstein's theory of relativity. And this is how the Hubble constant ties in with that theory. So the value of this number is measured, but we can derive from first principles the ways that it relates to other measured quantities.
The rate is speeding up. That means that this whole thing could be sort of boiled down into a single acceleration rate, right? Or is that not correct? In other words, 2 centimeters per year type of a number, right? Is it a constant? I mean, it's accelerating. So what is do you have a number?
Well, so this is a function of time. So throughout the universe's history, it has expanded at different rates, depending on these different types of energy in the universe. So so the scale factor A varies in time. It gets larger over time. And so you'll notice that these different terms in the equation depend on the scale factor A in different ways, meaning that they depend on time in different ways. And so at different points in the history of the universe, these terms have been more or less important, and they've caused the expansion to behave in different ways. So in the past, in the very, very distant past, the universe was dominated by this radiation term, and then for a period of time it was dominated by this matter term, and now it's dominated by the dark energy term. And the dark energy term is actually what causes it to accelerate.
That would still amount to a number of, like centimeters per year. You can still boil it down to that. I was wondering if you've ever done that.
Who, me personally? Well, it's definitely been measured. I wouldn't be able to say off the top of my head what it was in centimeters per year, but somebody, yes, that has been measured. It won the Nobel Prize in 2011.
So the expansion rate that's most commonly quoted is actually the Hubble constant, and that's 70 kilometers per second per megaparsec. A megaparsec is basically 3 million light years, give or take.
I one time did a calculation. If you take that as an acceleration, it works out to about 2 centimeters per year. If it can all be distributed to an acceleration.
Yeah, so what that constant means is if you have a galaxy that's 3 million light years away, on average it's moving away from you at 70 kilometers per second. If it's 10 megaparsecs away, it's moving away from you at 700 kilometers per second on average.
We have time for just a couple more questions for our panel, by the way.
So at that rate, what would be the moving away of, say, Jupiter and its moons? Because that we can measure more precisely than the standard candles, because from the eclipses and stuff like that. So have you measured that?
So the Hubble expansion of the universe is not relevant on very, very small scales such as our solar system, because our solar system is actually governed by being gravitationally bound to the sun. No, by Newton's laws. Yeah, this equation is only valid on very, very large scales. Yeah. Well, no, so the point of this equation is it's valid on scales larger than any gravitationally bound objects that exist.
How do you define gravitationally bound?
Where the gravitational potential energy is greater in magnitude than the kinetic energy.
So let's put it this way.
Twice the kinetic energy.
Yeah. Let's put it this way. To derive that equation, you assume that the entire universe is uniform. So the solar system, obviously not uniform. So these assumptions simply don't hold.
At what point when the expansion happens, at one point does gravity take over? Because Andromeda is coming closer to us, but everywhere else it's expanding. So what's the cutoff, if you know?
That's a great question. So the cutoff that determines whether an object is gravitationally bound actually varies based on the total mass of an object. So a very, very massive object like the system of the Milky Way and Andromeda can be gravitationally bound even though it's very large in distance, because it's also very, very massive. And so the gravitational pull between the Milky Way and Andromeda is so strong that they're still able to be gravitationally bound together even over a very, very large distance of, over a million light years, a couple of million light years. Wait. Yes, a couple of million light years. Now, for something like the solar system, the farthest out gravitationally bound objects to the sun are much closer, than something at the distance of Andromeda Galaxy would obviously not be gravitationally bound to the sun because the sun is not nearly as massive. So the cutoff really depends on the mass of the object. Time for one final question?
Is there anything working in opposite to the expansion of the universe, holding things together, aside from gravity in smaller systems? But I mean, overall, is there anything? I mean, in popular science things, you hear about dark matter. We talked about dark energy before. Is there dark matter that's holding things together?
Great question. Yes, so dark matter definitely does exist, and it does help to hold things together via the force of gravity. So gravity still exists on very, very large scales, and it's still relevant. Even though on very, very large scales, things aren't fully gravitationally bound to each other, but they still do interact gravitationally, and the force of gravity still does work against the expansion of the universe. All right. Well, thank you everyone so much for coming. We've really enjoyed being on this panel tonight, and we hope you all enjoyed the lecture and the Q&A. And please do pick up some flyers out there with the dates of our upcoming events. Pick up some posters that we have, exoplanet posters. I guess stargazing is probably over by now, but hopefully you got a chance to visit our stargazing event as well. So thank you all so much for coming.